would like to introduce Gabriel Skantze, who is a professor in speech communication and technology with a specialization in conversational systems at KTH Royal Institute of Technology in Sweden. Professor Skantze is interested in dialogue modeling with a goal to apply computational models to artificial entities such as social robots, as to enable them to have face-to-face conversations with humans. In 2014, Professor Skantze became one of the co-founders of the company called Furhat Robotics. Furhat is a social robot head with a highly expressive face that can cater for multimodal interactions using speech, eye gaze, head motion, and facial expressions. Over the course of those 8 years, Furhat Robot received many awards, and Professor Skantze continues to work part-time as a chief scientist in the company. So we are truly honored to have Professor Skantze present for us his work coming from a unique perspective across academia and industry.
I'm gonna talk a little bit more general first about human-robot interaction or conversational human-robot interaction, and then in the sort of second half of the talk, I will focus on the problem of how to model turn-taking in conversation. So to start, of course, the idea of interacting with machines through spoken interaction has been around us for a very long time, and especially in science fiction, it has always been obvious that that is how you would interact with machines in the future. So if you see Luke Skywalker and C-3PO here, it's obvious that they would talk to each other when communicating. Luke Skywalker wouldn't pick up a remote control and starting interacting with the robot, but they would talk to each other. So that has sort of always been clear, and now hopefully we are getting sort of towards this vision. If we look at robots, for a long time, robots were something that was very sort of dangerous machines, not very interesting, perhaps working in a factory assembling cars like this. And you were not supposed to be near because it was basically dangerous to be near a robot. And that is, of course, changing now. So we see a new type of robots that are being developed in academia and industry called social robots. And these are robots that are supposed to interact with humans. That's what social means, right? That you're interacting with other people. And they could be robots that both interact and do some manual work, like the robots on the left here. The top one is a robot that can help you to go to the bathroom. And below that, we see a robot that works in the small scale manufacturing, where you can grab the arm and teach the robot to do things. Currently, many of these robots, you can't really talk to them, but it's quite obvious that it would be nice to be able to talk to them. If you instruct someone, you would also be able to tell them what to do and not to do. If someone helps you to the bathroom, you would want to be able to say what you wanted to do and not to do, and so on. On the right, you see examples of robots that don't really do any physical task. And so the top, we have this Pepper robot, and below it, the Furhat robot that I would talk more about, which is actually only a head. And the Pepper robot does have arms, but the arms cannot really do anything. It cannot pick up things and so on. They're only there for social purposes. So you can gesticulate and point and so on. And the Furhat doesn't even have a body. It only has a head. So you might ask, why would I need a robot to interact with me if it cannot do any physical task? What is really the point? Why can't I just talk to my smartphone or my smart speaker or just some voice? Why do I need this robot? And one way of answering this question is to compare a phone conversation with a physical meeting. So it's kind of obvious to most people that the meeting that we see on the right here is the preferred way of interacting with each other compared to talking to each other on the phone. I mean, during the pandemic, this has been very obvious that we have sort of been longing to be able to sit in the same room and talk to each other. And there are many reasons for this. One is, of course, that we can see each other, we can see the faces of each other. But that's not the only thing, because we also have Zoom conversations where we can see each other's faces. But that's also sort of inferior to be able to sit at the table together. And one reason for this is, of course, that when we share the same space, we can very easily look at each other and see who is attending whom, who is addressing whom in this conversation here. So that becomes very obvious, and that relates to what I will talk more about later. That is the turn taking of a conversation, which can be quite hard to manage actually in other types of more online meetings. But you can also put things on the table that you can point to and talk about, and that's sort of the analogy to the situation we have here with the robot. So this really enables a conversation where we can be multiple parties talking, and we can point to things, and we can very easily see each other's where we are attending, etc. So that's why we believe that a robot holds a lot of potential when it comes to communication. If we then look at the face, why the face is important for conversation, we can look at it from, if we're building a robot, we can think of it from an output and input perspective. So from the output perspective, if we give the robot a face, the robot can show its attention through its gaze. So we know where the robot is looking. Is it attending me or some object on the table or some other person standing next to me? I can also read the facial expression, so I can see if the robot looks puzzled or if it looks happy, confused, etc. Also lip movements. So many people think that only hearing impaired people benefit from reading lips, but that's not the case. Actually, everyone benefits from reading lips. So if there is a background noise and so on, we benefit from reading each other's lips. From an input perspective, if the robot has a camera, it can detect people that stand next to it. So my smart speaker, I have a Google Home in my kitchen, but when I walk into the kitchen, the Google Home doesn't know that I'm there. So it wouldn't be able to initiate an interaction with me. But of course, if the robot has a camera, it's clear how many people are there to interact. It can also very easily see, is it one person or three persons that I'm supposed to interact with. You can potentially recognize people much more easy with a face than with a voice. And you can read their facial expressions. Again, do people look puzzled or happy, etc. And you can also see their attention. So are they looking at each other or are they looking at the robot? And that again helps with the turn taking, so we know, are they talking to each other or are they talking to the robot? Or maybe they are looking at some object that we are looking at together. So the face is, of course, really, really important for conversation. Again, that's why we prefer to meet face to face rather than talking to each other on the phone. So if we look at sort of, if we think the face is important, how can we give the machine a face? And here are some different options. So one quite common when it comes to robotics, actually, this kind of face, which is basically almost entirely static. And given everything I've told you now about facial expressions and gaze and lip movements, very little of that is in this face. So that's really limited in that regard. So it looks like the designers have sort of put more effort on other parts of the robot than the face. You can also go more abstract like this one, and that can be very expressive, but by giving it a more human-like appearance, you can also utilize all the signals that we know that humans use, and people can more immediately read the robot's expressions. And of course, you can go fully human-like, the Sophia robot here. And the problem with that is partly that it's very hard to match this extremely realistic appearance with realistic movement. And you get something called the uncanny valley. So it will give you sort of a zombie effect, or there is a risk that you sort of feel this zombie effect of the robot. And in addition to that, it's of course very expensive to put all these motors in the face and be able to sort of create these kind of natural movements. So that's also limited. And another option is, of course, to have an animated agent on a face, on a screen, like this one. And the problem there is we're sort of back a little bit to the Zoom conversation. And especially if you have several people standing in front of this animated face, it's not really clear who the agent is looking at. So if the agent sort of looks straight into the camera, everyone in front of the robot will feel like it's looking at them. So you can't really direct a specific person with a question in this kind of interaction. So based on this, we these sort of limitations, we developed this robot called Furhat at KTH. And the idea was to take the good things about animation, which is that it's very cheap and it's very expressive and very flexible. But we projected it on a mask with a small projector behind, and then you can put it on a neck, so it can actually move the head or move the neck while you're having the same animation, and you can move the eyes with by animation, and you can move the lips, etc. And this we continued to develop, and in 2014 we had a more developed prototype. We put a Furhat on top of it because we had to cover up all this technology. So that's why the name Furhat. And then in 2014 we started this company because a lot of people were interested and thought sort of how can you use this robot. And then eventually we created an even more sort of nice product out of this, and currently there are around 100 universities around the world that actually use Furhat in their own research. And one of the benefits here is, as you can see, you can actually project very different faces on it. You can make it into a male or a female or a child or a robot or a creature from outer space. So it's very flexible. And apart from the research projects that we have done or that I'm also doing in academia with Furhat and that others are doing, we have also explored more sort of actual sort of concrete use cases for Furhat. What would you use this for? One of these projects was a collaboration with Deutsche Bahn. So we developed together with them an agent. This is at the Berlin train station. So it was there, and it could answer questions about when your train leaves and so on, and also like where can I find the bathroom? Is there Wi-Fi in here, etc., etc. So that's kind of an obvious use case for a robot like this. Another use case is having actually used the robot to perform job interviews. So this was a collaboration with a company in Stockholm doing job interviews or recruitment firm. And together with them, we developed this robot called Tengai. They actually formed a new company for this robot. The idea is that the robot performs the job interview, and the idea is that the robot should perform the job interview in the same way with everyone and sort of try to reduce bias in job interviews. And so you can program the robot to really perform the job interview in the same way, because we know that humans have unconscious bias that affect how we, not only how we rate people, but also how we perform the interview. So if there is someone you don't think is fit for the job, if that is your first thought, you will probably signal that in your face, but a robot doesn't have to do that. So that's an interesting use case also. This is another project we are exploring now that is putting Furhat as a host on self-driving buses. So these self-driving buses are being developed, and they are actually running in Stockholm. Currently, there needs to be a human operator on board the bus to press the emergency stop button if something should happen. But nowadays, they actually serve also as some kind of host on the bus that people can ask questions. But of course, the question is what happens on the day where we actually remove that human, and there is no human representing the bus. And then the idea is that can we actually put a robot on board the bus that fills this role, that can answer question, but potentially also make passengers feel more safe on board the bus. So these are questions that we are exploring in this project. And going on to the challenge of building these kind of interaction, one of the things that I talked about, the benefits of doing this, is that we can have something called multi-party interaction and situated interaction with several people, but also with things in the environment that we talk about. And one of the test beds that we have used quite a lot is this game where we have two people playing the game with the robot. And the idea is that you should sort these cards depending on some sorting criterion. So in this case, it's buildings in Stockholm. You should sort them based on how tall the buildings are. And you should discuss the solution together with Furhat. To do this, you need, of course, sensory data. So you need to track people. You need to track where the audio is coming from, where the objects are, and you need to sort of model this. So this is the robot, and these are people, and these are the cards seen from above them. And then based on this, you can sort of direct the robot's gaze towards the cards or people, etc., etc. So this is, of course, something that is very different from developing a smart speaker or a chatbot that you have to do this. So I just want to play a short video where you just to get an idea of what the conversation looks like, and that the conversation in this kind of setting is very different from when you talk to your smart speaker, where you mainly issue commands or ask questions to it. This is more of an ongoing conversation playing this game.
Jag har hört att Italien har många guld i fäktning och cykling.
Ja, men de är väl ganska bra, är de inte det? Kanske ska ligga med här borta. Kanske.
Ja, jag vet inte.
Danmark vet jag inte
Danmark,
hur bra de är.
Kanske med vintersport, men alla andra länder, Portugal, Italien, de är inte så bra med vintersport.
Nej.
Grekland.
Men Finland har väl mycket. Är inte Finland bra på vintersport? Vad tror du?
Finland har ju mycket snö. Så de borde vara bra på vintersport.
Ja, jag tycker också det. Vi lägger dem ganska högt här borta. Men kanske inte lika högt som Italien. Danmark kanske.
Jag tycker också att det verkar bättre att ha Finland där.
Ja, det tycker jag också.
So this scenario again is something we use because we think it sort of creates a quite natural conversation or discussion. And it's also very open who should take the turn, who should be the next speaker in this conversation. It's sort of sometimes optional for the robot to say something. Sometimes it has to say something because you get sort of a clear question from someone. Sometimes you can take the initiative and try to steer the conversation, etc. And this relates to the sort of topic I want to sort of start talking about, and that is turn taking in conversation, and something that we have been doing a lot of research projects on, something I personally find a very, very interesting problem. And it's something that you typically don't think about. If you have a written chat, it's obvious who should speak next at what point, because you type something and you hit the return button, and then it's the other person's should say something. But if you look at human conversation, in spoken conversation, you can look at people talking, and you can look at the data set, for example, if you record people talking, and you can see what does it look like when someone stops speaking and the other person starts speaking. And one thing you can do is to look at the length of this gap between the turns. And that's, people have done that, and you can make this kind of histogram. So it's how frequent are different gaps. The positive gaps are if there is a gap, so this is 0 and this is 1 second. Negative ones is if there is an overlap between these. And what you can see is that very often the gap is very, very small. It's like 200 milliseconds. That's the most common response time here. And 200 milliseconds is really little. It's very, very fast. And that's sort of an interesting question. Then how do people manage this? Because you don't only have to know that it's your turn to speak, you also have to, of course, figure out what to respond. So that's very interesting, and something that has sort of intrigued researchers from psychology and linguistics, and then also us, of course, that try to model this computationally. So if you look at how turn taking is typically handled when you talk to your smart speaker, for example, it's not like that. So let's say if someone says, could you play Waterloo by ABBA? And then the system says, sure, here it is. Typically what you do is that you use a silence threshold. So you say, okay, after about 1 second of silence, the system should respond. So this is clearly much more than the 200 milliseconds that we saw in human-human conversation. And what would happen if we just reduce this to 200 milliseconds? Well, what happens is that you would just trigger this as soon as someone makes the slightest pause. And the system would say, so it would be like this: could you play? Excuse me, I don't think I understand. And you sort of get this interruptions basically by the system. And even if you have 1,000 milliseconds, you will also interrupt users because people can make pauses that are longer than 1 second. So using silence like this as a means for taking the turn is not a good idea. But it's sort of the best thing we have. It's an easy solution. So silence is not a good cue to shift turns. And the question then is how can people have 200 milliseconds then? Well, they must use other signals than silence. And that's what researchers have found since the 1970s, is that there are a lot of different signals actually. So the idea is that when someone is speaking and we are shifting, there is something called a transition relevance place where you can take the turn. You don't have to, but you can take the turn. So it's like a traffic signaling. Here is a green traffic light saying that you can take the turn now. You don't have to wait, you can take the turn. But if this person needs to take a pause here, you can have sort of a red traffic signal saying you shouldn't take the turn. I want to keep the turn until I give you a green light. So the question is, what do these green and red signals actually look like? Because we don't have green and red lights in our face. People have found that it's actually using a lot of different signals. So we talk about turn yielding cues, which is the green light, and then turn holding cues, which is the red light. You find it in syntax. So if you have a complete grammatical sentence, you're typically more likely to yield a turn. If you stop in the middle of a sentence, so I would like to buy, yeah, it's more likely to be incomplete. It's a red light. But you also use prosody, so the way you are speaking. You can have a rising or falling pitch to signal that you're yielding, or a more flat pitch to signal that you're not yielding. Likewise, for the intensity and duration also matters. Breathing, so if I breathe out, it's more likely to be a signal that I'm yielding the turn, and if I breathe in, it's more likely to be a signal that I'm holding the turn. Gaze also, if I look at the other person, it's sort of signaling that I'm yielding the turn. If I look away, it's more likely that I'm thinking about what to say next, so it's more likely to be a signal that I'm holding the turn. Gestures can also be used. So what researchers have found also is that the more signals you have, the stronger the signal. So many turn yielding cues, it's more likely to be yielding, and the other way around. So this is very nice, of course, from our perspective. So we could have a robot that have all these different signals actually be able to use these cues. That's great. So how do we do that? So again, we can look at this from an output and input perspective. And let's start with the output. How can the robot display these cues to show its intention about whether it wants to take the turn or not? So in the card game scenario, let's say we have this scenario. The user says, what do you think about the tiger? And the robot knows that it needs some time to actually produce a response. Maybe it's accessing some resources or something. So you have this kind of long response delay here that you're creating before you can say, I think the tiger is faster. The problem with this kind of long response delay is that the user might get confused and say, hello, because you don't know that the robot is intending to take the turn. So you get this interruption and you get confusion. One way of mitigating then is to produce a turn holding cue of some sort to show that I'm actually claiming the floor here. And when we were running this card game scenario at the Technical Museum in Stockholm over a week, we randomly tried different turn holding cues to see would they have an effect on people, even if they are very subtle. And it did. So we tried, for example, does it matter whether the robot at this point is looking at the user or looking away? So if it's looking away, that should be a signal that you are taking the turn. But if you are just looking at the user and not doing any other signals in the voice or the face, there is a 35% risk that the user will interrupt the robot here, and there will be confusion in the turn taking. You don't want that, of course. But if you produce, for example, a filled pause, like or you let the robot smile, or you do an in-breath in the robot, which we simulated by playing an in-breath sound and moving the mouth a bit, you actually reduce the risk of the user interrupting. You can also do gaze aversion. So if the robot looks away, even if we do nothing in the verbal or facial, you get to 25%, so a reduction in user interruption risk. But if you combine this, so you do both gaze aversion and produce a filled pause, for example, you reduce it even further. So you reduce the risk to 15%. So it shows that these signals, even if they are very subtle, and even if we haven't told anyone that, well, you know, if the robot does this, it means this, people automatically understand these signals because they are human-like signals. So that's very interesting. From the other perspective, can we also detect these cues if humans use them? Yeah, so we looked at the data we had collected, and we looked at different points in time where people, for example, is holding the turn. So this is a case. Someone is saying, yeah, that's a case where robot shouldn't take the turn. Like this, and it's looking at the table, that's might be an opportunity to take the turn. But if someone looks up at the robot and says, what do you think? That's an obligation for the robot to take the turn. It would be very strange otherwise. And then we used all the different sensory data that we get, that the robot gets, like the user's head pose, their prosody, the words they are saying, whether they are moving the cars at the moment, what they have said in the past in the dialogue. And we feed that into a classifier, and we can try to predict this. And if we only use one of these, like the head pose, we get 70% correct. But if we use more, head pose and prosody, we get 79%. And we use all of them, we get like 85%. So it shows that, again, the more cues, the stronger the signal. And it's sort of also a lot of redundancy in these different signals that can help the robot to know whether it's supposed to take the turn or not. So that's sort of, again, an argument for this kind of multimodal interaction that you allow for when you have a human-robot interaction. Currently, we are interested in how can we go beyond this. So if you look at human interaction, as I said, we know that people can take the turn with a very, very short sort of gap here. And our current system can't really do this. It's even if you can detect that you should take the turn, it's so little time to actually produce a response. And it's the same for a human and for a computer. So what humans do, of course, is to try to predict. So while the other person is speaking, we're trying to make predictions about the future and see, what do I think they are gonna say in the next second, so that I can start to plan my response. And then eventually, when I get this sort of signal that person is yielding the turn, I'm ready to start responding. And we know that this is what humans do to some extent. And the question is, can we also make computers do this thing of trying to predict what you are about to say, basically. So this is a very interesting thing that we have we are looking into in different research projects. One of the approaches that we have tried is to we take the data, so this is speech from two people, and we just slice it up into short frames. And then at every frame, we feed this into a neural network that is making a prediction about the next 3 seconds of the conversation. So we are trying to say, in this case, it's very easy. We are trying to guess whether they will be speaking or not in the next sort of time window. see here. There you go. And then we feed it with the sort of true data of whether the person were actually going to speak or not in this future time window. And what we get is actually quite nice predictions. So this is an example. So let's say that we are at this point in the dialogue, with the red line shows here, and the green bars shows the model doesn't know anything about the future. I just show the future, what the future actually looks like. And the green bars or lines here is the probability that the model predicts of the person whether the person is going to speak or not in this future time window. And we can see that it actually assigns a higher probability here for this person to be speaking compared to this person. So it makes a fairly good prediction. And it means that if we are at this point in the dialogue, the model can predict who is likely to be the next speaker, which means that if the robot uses it itself, it can sort of guess that this is a good place to take the turn. This is a good place for a turn shift, right? Whereas in this case, this is a good place. This is not a good place for a turn shift because the model predicts correctly that it's more likely for this person to continue speaking compared to this person not speaking. So that's what we call then a hold. So that's quite nice that we can do this kind of prediction. And another type of prediction we are doing is more in the sort of word domain of what you will, not only whether you will talk, but also what will you say. So this is another experiment we did. We built a model that can try to predict what you will say. So if the system says, how long was your trip? And the user starts saying, I'm not sure, it may have, then the model can start what we say projecting different futures. So the model starts to guess that you might say maybe it may have been a week or been about 2 months. All of these are just the user is continue speaking, and we can't really see in this future any turn shift happening soon. So we don't have to prepare a response yet. But as we get a little bit further in the dialogue, and the user says it may have been about, and we start projecting the future, we can see that the model actually sees that in several of these projected futures, there is a turn completion here. So it's likely to occur soon in many of these projected futures, which means that the system can start sort of preparing a response already at this point, even though we are not there yet. And of course, if there is no turn completion, it doesn't have to say this, but it makes it possible for the system to actually sort of prepare a response. So this is sort of a line of research that I think is very exciting. Okay, but to wrap up a bit, we have talked about turn taking in dialogue as a coordination problem. So how do we know when we are supposed to speak and the other person is supposed to speak? And we have seen that doing this benefits from multiple modalities. We use linguistics cues like what we are saying, the prosody, the way we are speaking, and the gaze also is important. And this means that the face is a very important coordination device. And that sort of explains why we prefer face-to-face interaction over other channels. And we also like physically situated interaction because we can have a multi-part interaction where it's more easy to see who is speaking and who is addressing whom, etc. However, current conversational systems lack both understanding of these signals and generation of these signals. So this is a very important thing to research. And we also argue that in order to achieve this kind of real-time coordination, we can't fully do that without having a machine that can be able to some extent predict the future online during the conversation. So if you think this topic of turn taking in conversational systems and human robot interaction is interesting, I can recommend you to read this review that I recently published in the journal Computer Speech and Language. where I discuss this in depth and look at the research tradition, but also on the research tradition of human-human turn taking and sort of putting that in this context. So with that, I would like to end and say thank you for listening to my presentation.